And so question 9 from the 2016 Advanced Higher Mathematics of Mechanics. Here we go, 7 marks, circular motion. Bicycle going round a circular track. A velodrome has a circular track of radius 30 metres. No, it doesn't. How can it? Must have a certain width. There will be one circle of radius 30 metres, but it must have other ones on either side of that, so it must be the bicycles sticking to a circle of radius 30 metres, banked at an angle of 32 degrees to horizontal. Coefficient of friction, certainly, it will just slip off. 0.3. The bicycle's got to get to its maximum speed without slipping. Right, what's that situation? I'll put it down here. So we've got banking of 32 degrees. There's a bicycle on it. I'm not saying that's necessarily the angle of the bicycle for maximum speed. So what are the forces acting on it? Well, if it was just moving along without any forces acting on it, it would continue in a straight line and go shooting off tangentially. So the forces would be, 1, there's the weight of the bicycle itself. Then for the contact forces with the surface, there's 2 components you use. There's the normal force, which resists that sinking into the surface, and there's the force of friction. Because what's making this bicycle turn in a circle isn't some gravitational force or some rope tied onto it pulling it in towards the centre. There's no centripetal force like that. What's making this bike curve is the steering. Now, you go along in ice and turn the steering handle as much as you like, just keep going in a straight line. You won't be able to turn it unless there's a frictional force, and it's this frictional force which enables it to continue around a circle, which means this frictional force isn't acting up the slope, it must be acting down the slope. And those are the only forces on it, but they're not balanced. If that bicycle wasn't moving, then obviously that would just fall over under that situation. What's happening here is there's an unbalanced force, and it's that unbalanced force that provides that centripetal force which enables it to go round in a circle, that provides that force which is MA or mv squared upon r. Right, now it's just a case of, well, how do we work out this V from that diagram? Well, resolve the forces for equilibrium, and you've got 2 choices. You can go parallel and perpendicular to the plane, which is usually quite handy because those are parallel and perpendicular, so you get one of them and not the other. Or, since this motion is in a horizontal circle, resolve them horizontally and vertically. So I think I'll resolve it horizontally and vertically first. There's actually 2 ways. Well, there's actually 3 ways. There's a third way, which I'll mention at the end, so this will be quite long. So, resolving them horizontally. So the sum of the forces across the way, I'll just put it down that way. What have we got? Well, acting across the way, it's not this. That's the unbalanced force, that's the result of this. The weight's not involved in that. We've got the friction and we've got this part. So for the friction, oh, it's not very good, this diagram, that'll be 32 degrees, by alternate angles. And for the normal, that'll be the 32 degrees. So acting across the way, notice both of them are going the same way. So that means you've got N, and this portion is away from the 32, so that's N sine 32 degrees, plus F, and that's adjacent to the 32, plus F cos 32 degrees, doesn't equal 0, because it's unbalanced. The result of them, instead of coming to 0, because it's not a static equilibrium, equals this force. The unbalanced force provides the centripetal acceleration. And then resolving the forces vertically. Well, vertically you've got a part of N is going up the way, and that part's next to the angle, so it's N cos 32 degrees. F is acting down against it, so it'll be minus F, and this part is opposite the 32, that's the sine 32 degrees, and all of W, minus W, and that is balanced because it's not moving up and down the way. That does equal 0. Next part would be this. The force of friction is the coefficient times the normal reaction, and if it's on the point of slipping, F will be at its maximum value then, which is the coefficient of friction, which is 0.3 in this case. It's equal to 0.3n. And it tells you the radius of the track is 30. So feeding that into this, I'll get 2 equations. So the first one is going to say n times that plus 0.3 of n times that. So you can take the n out as a common factor. So n sine 32 plus 0.3 cos 32 is equal to mv squared, and we know r is 30. There's one equation. Similarly for the second one, that'll be 0.3 n, so take that out as a common factor. N cos 32 degrees minus 0.3 sine 32 degrees, and I'll just take that across the other side, and of course the weight is equal to mg, and there's another equation. Now it's only v that I want, and there's this m and there's this n, but they'll disappear quite conveniently as soon as you divide them. So if you do 1 divided by 2, this side here, the n's will cancel out, and you've just got this big blob here, sine 32 plus this bit here, which is just a number after all, is equal to, and then this divided by this, the m's cancel out, and you're left with v squared over 30. I'll just leave that as g. No, I won't, I'll put it back as 9.8. So there's only one thing you don't know, v, which means you can find it. So v squared will be 30 times 9.8 times whatever this comes to. I'll just put it all in it. You probably would have worked it out. I'll just write it in very quickly. Like that. And then you just press the buttons, you'll get the answer to this part. Or, if you didn't want to press the buttons and get the answer to that part, you could just do the square root straight away. Square root of this whole thing. And then we'll get the answer in one go. And once you've typed it in, which took a wee bit of time, blah blah blah, out comes the answer, 18.293 and so on. So that means the maximum velocity, because we used this part here, the maximum velocity is 18.3 metres per second. Oh, and of course the marking was, there was a marking for each of these resolutions of the forces horizontally and vertically. There was a mark for, so probably in this form here, once you've introduced the coefficient, so there'll be a mark for each of those equations. There was a mark for the way you dealt with it by dividing, and then finally there was a mark for evaluating it. So that's 4 marks so far. And then the second part is, once you've reached that speed, you carry on for 5 minutes, how many laps would you do? Well, that's just a matter of time, distance, speed, isn't it? There's different ways you could do it. You could find how far would you go in 5 minutes at that speed, and then divide it by the circumference of the track. So, you could work out the distance you would travel in that time, which would be 18.3 times if it's 5 minutes, that's 5 times 60. I'll not cancel anything down just now. That'd be the distance you would travel in metres. Work out the circumference of the track. That'll be 2 pi r. So that's going to be 2 pi times 30. And then the number of laps will be, well, how many of them fit into that? So the number of laps will be 18.3 times 5 times 60 over, and of course that's just 60 times pi. So this 60s will cancel out, so I'll even put them into the calculator. And that gives you 29.125. So that means you'd manage how many full laps? Well, that's 29 laps. So that equals 29 laps. So that would be, there's the 1 mark. There would have been the 1 mark, I suppose, for working out the distance travelled, but you didn't, strictly speaking, need to work it out because you can put it together in a calculation and save some time. There's certainly 1 mark for the final answer. And the other mark would be for working out the 2 appropriate things, the distance travelled and the circumference. Another way would have been, but you probably wouldn't have done that, would have been to work out the time for 1 lap from the circumference and then see how many of them would fit into the 5 minutes. But in the end, the calculation would still come to this part here. Now, even though this motion is in a horizontal circular plane, that doesn't stop you resolving it parallel and perpendicular to the slope. You can use any directions you like. You'll get exactly the same answer. So I'm going to do that again by resolving along f and n, parallel and perpendicular to the slope. But then at the end I'm going to do a much quicker way of doing this. It'll have far less working in it. So what happens if you were to resolve it along F and along N. So there's no components involved in those ones. You're still going to have your sines and cosines will come in, because once they become nicely orthogonal to the resolution, they become squinty. Swings and roundabouts. So for the weight, if that's 32, that would be 32, that's its complement, so that's back to 32 there. So I draw the weight again here. So the components of the weight would be perpendicular to it and parallel to it, where that's a 32. This one, parallel to it, perpendicular to it, where alternate angles, that's a 32. Right, ready to go. So this time resolving it, instead of in the direction of this plane of motion, just resolving it in any direction you like. So I'm resolving it onto the slope of it. So resolving the forces, parallel first of all. Right, what have we got? Parallel to the plane, well obviously you've got F. Also acting that way is part of the weight. That's this part here, opposite the 32, that's the sine, and it's going with it, so plus W sine 32. Doesn't come to 0 because it's not balanced. It gives a component of this resulting force. It will give this component of it here, which is next to the 32, so it'll be mv squared upon r cos 32 degrees. Resolving it perpendicular to the plane. Well, obviously you've got n then, and there's no f involved this time, but part of w is going that way. This is the part of w next to the angle, so that's the cosine, but it's going against it. So minus w cos 32 degrees doesn't come to 0 because it's not balanced. There's an unbalanced portion of this force here. There's an unbalanced component, and that unbalanced component gives you this part here. That's opposite that, so that's the sine. So it'll be mv squared upon r sine 32. So you can see you're ending up with the same things. Now the next bit would be this. Maybe I'll just, same as before, I'll tidy this up. I'll tidy that up to read F equals. So F's going to equal, when you take this across, that'll be a minus. So it'll be mv squared upon, well, we know that that's 30, cos 32 degrees, but minus, and that's mg, I'll just leave it as a g, sine 32 degrees. There's one equation. And same with this one, I'll take that across. So I've got mv squared upon 30 sine 32 degrees, but that'll be plus mg cos 32 degrees. And then there's a connection between the two of these at the point of slippage, which of course is that the force of friction will be the coefficient times the normal reaction. That'll be 0.3 n, which means this is equal to 0.3 times that. So we'll just write that out quickly. Like that. Now obviously every single term has got m in it, so the m's will cancel out. And then taking the terms with the v's together on this side and the other terms on that side, when the m's have gone, we've got a common factor there of v squared upon 30 times cos 32 minus 0.3 sine 32 degrees is equal to, they've now got a common factor of g, and I'll just put this one first here, so that'll be, the m's gone, remember, that'll just be sine 32 degrees plus 0.3, and the m's gone, the g's gone, cos 32 degrees, and there you are, back to the other one, same as you had before. V squared is going to equal, I had the g over that side before, it makes no difference, V squared equals 30g times etc, etc, because that's now the same as the previous one. But what's a bit messier than resolving it in the plane of the motion? But it didn't actually matter which way you resolve it, you'll always get the same answer. However, there's an easier way than either of those two resolutions. And that way would be just to use the contact force with the surface rather than its two components, the normal and the transverse frictional force, by using the angle of friction. If an object sitting on a surface isn't moved, then the normal reaction just supports the weight of it. If you attempt to move it, there's a frictional resistance to it, which means taking these two components together means that there's a contact force that looks like this, which has these two components, the normal and the frictional force. And once that frictional force reaches its maximum value, F equals mu n, then it'll start to slide. At that point, once that reaches that, this contact force will have a certain angle, the angle of friction, and the tangent will be F over n. So the tangent of that angle is the coefficient of friction, as you knew anyway. But what you could do here is this then for this diagram. You could say, well, I think for this diagram I've got my bicycle. It's on the point of slipping, so this contact force must make an angle of theta to the normal. So I've got the normal. It must make an angle of the angle of friction here. So what is that angle of friction? We'll just put theta there. So tan theta would equal 0.3, which means theta will be the inverse tan of 0.3, which is 16.699, which is 16.7 degrees. So now I'll take my diagram. I've got the weight acting down the way. I've got, if this is 32, then that's 32 and that's 16.7, which means this contact force is at an angle of the sum of the two of those, 48.7 degrees to the vertical. And now, and of course, the resultant force of all of that is still that MA, where you've got that centripetal acceleration, which is v squared upon r, so mv squared upon r. Now we can do that. What are the sum of the forces horizontally? Well, none of the weight. So the only one you've got is the horizontal component of C. That's the side that's opposite the 48. So this just says C, if you wish to call it that, you might call it R for that reactive force instead of C for the contact force. That C sine 48.7 degrees is the only force that's acting in that direction, so that's the unbalanced force that provides mv squared upon r. That's one equation. Might even go further by saying I know that r is 30. Now we'll take it vertically. Now vertically, the component of that, because it is heading up the way is adjacent to the angle. So that means C cos 48.7 degrees minus the W should equal 0, because there's no vertical movement there. So there's another equation, or maybe I could tidy it up first. Maybe we'll tidy it up first. So you've got C cos 48.7 degrees equals mg. Now there's only one thing I need to find, and that's that v, because everything else, when I divide them, will cancel. If you do 1 divided by 2, you'll have c divides out c, sine over cos makes tan, so I've got tan 48.7 degrees, m cancels out m, and I've got v squared over 30g. And so there you are. V squared will be 30 times 9.8 times the tan of 48.7 degrees. Or, in one go, the square root of that. And there it is, 18.293 and so on, so 18.3 metres per second, as before. Given that air resistance can be ignored and the cyclist is treated as a particle, what other assumptions have been made? Well, the assumption, I suppose, is that the cyclist stays in a circular plane of radius 30 and doesn't move up and down. The track must have a width, so the cyclist must stay in a horizontal circular plane. Oh, I'll have to write out. Cyclist doesn't travel up and down, as you see them do in these velodromes, travel up and down track, which they tend to do, but stays on a circular, a horizontal, maybe I should say, a horizontal circle of radius 30 metres. There's the final mark. And I should mention again, this was a much quicker way than the other methods of resolving it, simply because in this case you could use the contact force since it was at maximum friction, since it was on the point of slipping, because that's the only time that angle of friction would apply.